DC voltage is just voltage that's constant. It doesn't change in time. If we tried to draw it like what the waveform of DC looks like, it would just be pretty much a straight line. Maybe we can put a 0-volt reference in here to say, so this would be some amount of positive DC voltage. And it could be negative DC voltage. That would be below the 0-volt reference. As long as it doesn't change back and forth, it is DC. Pulse DC then is another type, and here you could say, as long as the volt, we've seen this with our 555 circuit, you could just get little pulses out. We could still give ourselves a 0-volt reference, but here the voltage is changing in time, and it's high, for a little bit here, then it's low. As long as it doesn't go and reverse polarity, as long as it doesn't go negative, then it's in the category of pulse to DC. AC voltage, let me get my 0-volt line in here. AC stands for alternating current, which means current is going to be going one way and then reverse direction at some point in time. So it's possible to have, if we kept the same waveform as we just did, this would be AC, where we have positive voltage, but then it reverses polarity. We now have negative voltage, and back and forth. So this is an AC waveform. It will have that reverse polarity. Voltage will be going positive and negative in the same waveform. So it'll be going current will be going one direction here, then it'll be going the opposite direction when the voltage flips polarity. So this gets us into this whole discussion with waveforms. There's not much of a waveform discussion in the DC course because there's not much of a waveform. It's just a constant voltage for the most part. And like I said, it could be here, it could be a constant voltage that's negative. Don't forget that. If the voltage changes in time, but doesn't change polarity, you've got pulse DC. If it changes in time and does change polarity, you've got AC. So those are the three categories: DC, pulse DC, and AC. It does not have to be this shape of what we would call a rectangular or a square wave, and maybe if it's 50% duty cycle, it's a square wave. It could be other shapes, so let's look at some of those other shapes. Pulse DC, again, it doesn't reverse polarity, so let's look at this. Some other classic shapes, a ramp perhaps, and it could ramp up and then drop down. That ramp could be symmetrical, and then we would call it a triangle wave. Oops, I'm trying to do equal time up and down. Okay, triangle wave. You could have I think I kind of drew it there. If you have a symmetrical rectangular wave, this is a rectangular wave, but if it's symmetrical in time, which means there's equal time for the pulse width and equal time for the space width, we call that a square wave. So things like that, we would call this maybe a sawtooth is another term for it, or a ramp. 50% symmetry, they would refer to it as symmetry. There's not really a duty cycle associated with sawtooth waveforms, but there's symmetry, and if it's equal symmetry, then it's a triangle wave, like we said. You can have rectangular waves that have time symmetry. This is the time across the x-axis. So if they're symmetrical in time, it's a square wave. I can just quick sketch another one here. Of course, it doesn't have to be symmetrical in time, and you've seen that where maybe the pulse width is different than the space width. And so that would be a rectangular wave that's not symmetrical in time. And of course, those same shapes can go positive and negative. So, we should make sure we understand that. I mean, this sawtooth or this ramp could do something like that. Now it is an AC waveform. It's going positive and negative. We could have a triangle wave that does the same, right? So, sketch a bunch. I think you get the idea. There's my 0 volts. This could be going, a square wave could be equal time. Yep. And so on. So, just to finish out our examples. And actually, I'll get a little more room because I have more wave shapes to show. If I can get this thing drawn here. Okay. So, yeah. All right. Let me scoot up a little bit. Let's see. One of the main wave shapes we'll spend a lot of time on is a wave that increases and decreases at a sine function rate, and it's a sine wave. And it's a naturally occurring thing in nature too. We'll talk about all the different ways that sine waves happen in nature, but the voltage, if it's voltage for us, it's going to increase rapidly and then slow down and then decrease. And then it's going to increase rapidly in the negative direction and then slow down. So there. So that's a sine wave. And it's, in this case, I drew an example of an AC sine wave. I could show you a pulsed DC example where it doesn't go negative, it just keeps, we'll get into this. So it still has that sine function, but it repeats like this. So this would be increasing and decreasing at a sine rate, but it's pulsed DC. I mean, yeah, pulsed DC. Yep. So we'll get into that down the road. But yeah, so these are some classic waveforms. The waveforms we're going to look at are all what you would call periodic. They repeat in time. So there is a definitive period, which is the amount of time in seconds it takes to complete one cycle. So all the waveforms we look at will have that. And we could look at our examples here. I think you can see it's pretty universal. We could grab another color here. Like here's the period for this waveform right here, right? How much time does it take to complete a cycle, right? You can pick any point and then on the waveform, and when it happens again, so it doesn't matter which point you pick. If I pick 0 volts on a rising edge here and then look for 0 volts on a rising edge to occur again, okay, I've got it. And that's that's my period. Okay, so I'm just picking through here, just giving you that idea of how you do this. If this is up on your scope screen, you just get your cursors out, vertical cursors, and you can measure the time it takes to complete one cycle. Okay, so that's again, and we'll be doing that with your analog discovery. I guess the next thing might be to create a bunch of different waveforms and have a look at these basic parameters, be able to do these measurements with that. Now here I'd have a period for this sine wave, right? From here to here, that's the period. Careful, over here it would be just this, because it repeats after one of those positive half cycles, you might call it. We'll get into that. And if you know the period, I think you do know the frequency, right? Because frequency is just another way of talking about sort of the same parameter. It's 1 over the period. And period is 1 over the frequency, right? Because the period's telling us how much time it takes to complete one cycle. How much time does it take for the waveform to get all the way through one cycle? If we know that, then we also know how many cycles will happen in 1 second. So frequency is how many cycles will happen in a second, and period is how many seconds it takes to complete one cycle. So cycles per second for frequency, and seconds per cycle for period. Okay, there's a couple other parameters maybe to look at, sort of get our heads around. I think we know a lot of them. The fact that we have voltage changing in time means that it gets a little more complicated now. In other words, we only had to talk about, you know, one parameter for this waveform over here. 10 volts. What do you have? I have 10 volts DC, you know, for my source. Doesn't change. So that was the end of it. And now in the AC course, it's going to be a lot more to talk about because voltage changes in time. So some of the parameters that we have to get comfortable with, well, we already mentioned for frequency, period. There'll be things like peak voltage, and that's just what you would think. It's where is the uppermost voltage? What's the maximum voltage it goes to? Okay. So that would be, if I go back down to my sine wave here, here's my peak voltage, right? Peak to peak, that's the distance between the two peaks. So we have that to look at. Peak is just amplitude. Peak to peak is the distance between the peaks. Okay. And you can see it in other waveforms too, right? I mean, what those would be. Offset. Let's talk about that one. Offset is the center of the wave, okay? So you have to look at the wave, and if it's changing, if I can change to a different color here. So if you're talking about the center of a waveform, let's see. Well, let's pick an easy one. Right here. Here's my center. It runs right down through. The waveform centered on 0. So I would have 0 volts offset. There is no offset. Okay. But if I push the waveform off being centered on 0, however much I offset it, that's the offset. It's always the center, the midpoint between the two peaks. Yeah. So you have to know the two peak voltages. So maybe I can just quickly put another example here. What do we want to do? Should we create a little more? I don't know. But I could offset this waveform. I'll stick with this. I'll stick with this one here, I guess. So I just grabbed it randomly. I could offset it by a certain amount of voltage, just push it up. So if I put if I centered it on something like, maybe I'll just put 2 volts here. So I'll just say now I'm going to center it on 2 volts, and I'm going to push it up. Let's say this was you know, -4 and +4. This is going to be tricky to do here. It's going to get crowded. But I could push the whole waveform up, and now my new bottom peak would be at -2, and the upper peak would be at 6. So I could do this, and I've added offset to it. So we'll try to experiment with this stuff with the analog discovery. I'm just trying to give you a little sort of intro to all of this. So do you see what I'm doing here? My new center of my waveform runs down through here, and it's centered on 2 volts. So the offset is 2 volts. And that is the midpoint between 6 volts and -2 volts, right? If I haven't made a complete mess of this. Right? Because 2 volts is midway between -2 and 6. Think of a number line. And there we have it. So that's offset. It's the center. I can offset the sine wave too. I could do that. I mean, if this had like a, let's just keep with 4 volts that we did, you know, right? I could do the same thing. I could push it up. I could push it down. I can have negative offset. But if I pushed it up to maybe a 2 volt centered sine wave on 2 volts, the world's worst sine wave, same game. And I could have a 6 volt peak. So offset doesn't belong just to square waves or any one waveform or wave shape. So we could have the same thing. So we can push waveforms up or down. They can be centered on 0, in which case the offset is 0. But they can have offset too. Okay. Yeah. And let's see. A couple other parameters maybe to talk about. You know, if they are centered on 0 volts, we would call that amplitude symmetry. They're symmetrical in voltage. Okay, let's go back and just highlight just a few more parameters. What do we have? Frequency, period, peak. What's the peak voltage? What's the peak to peak? What's the offset, if there is any? Average voltage, we've mentioned that before. And that's simply if you take all of the voltages that occur in time and average them together. Overall, as this waveform is occurring, what is the average voltage when you just put all the voltages that occur together and average them out? So that's pretty self-explanatory. And then there's Vrms, and that is a value for any waveform where you take all the voltages that occur in the waveform and all the instantaneous voltages, you square them, and then you average that. So it's the average of all the squared values of voltage that occur, and then you square root it. So it's the root of the mean, which is the average, of the squared values. So you have to square the waveform and then take its average. So the waveform will change. When you're doing the RMS, if you did it in steps, you would take the waveform and then square all of its values, so it would change. And then you would take the average of that waveform, and then you would square root that. So that's RMS, and that's a little headier, a little trickier to sort of grapple with. But yeah, that's an important one. Let's see, what else? What else can we say? There's something else I wanted to mention there, but yeah. So all waveforms will have these values, and we'll be getting sort of oriented and good at solving for them. And then there's some things that are peculiar to some waveforms, such as, I mean, we've already looked at things like, you know, pulse width and space width occur for rectangular waves, but obviously they're not a thing with sine waves or triangle waves. There's no such thing as pulse width and space width. So that's unique to them. We do have a need sometimes to look for instantaneous voltages, so we'll be looking into that. Instantaneous voltage is asking the question, if I draw a new waveform here, let's see. If I draw a sine wave, there might be a question of what is the voltage right here? So that would be an instantaneous voltage that we can calculate. We can solve for that, but it'll take a little bit of doing. And probably get into that in another video, in another session. Let's see if there's anything else. Yeah, I think we're pretty good. You'll hear us talk about time symmetry. So you can have amplitude symmetry. If there's no offset, you have amplitude symmetry. And we'll also have the time symmetry if it, for example, this one looks, the square wave is symmetrical in time, isn't it? Equal time here and here. Sine waves are symmetrical in time. They have that built right in because it's a sine function. Triangle waves are symmetrical in time. Square waves are symmetrical in time. So square, triangle, and sine all have that time symmetry built in. Okay. I think we'll save this instantaneous voltage for another video, but it is an important parameter. So again, what we're trying to do here is sort of get you to see the waveform parameters that we have to deal with. Now that voltage changes in time, we're just going to look at quite a few things that we have to calculate, that we have to use now. It's not as simple as I've got 10 volts, it's what is that 10 volts? So you always have to specify with subscripts. Is that 10 volts peak? Is it 10 volts peak to peak? Is it 10 volts offset? Is it 10 volts average? Is it 10 volts RMS? Is it an instantaneous 10 volts? All those would be different waveforms, right? And how often does it occur? And so on. How long does it take till it repeats? So you see, when voltage starts changing in time, then it becomes a lot to characterize it. And these are the parameters that we'll be using. So, okay. There is one more I was kind of hedging on mentioning. I guess I'll mention it. The time here for this sine wave is the period. There is a certain time right here that it takes to get to this voltage. And what we're going to also understand about, this is something peculiar to sine waves, or specific, I should say, to sine waves. We're going to be able to identify points in time for sine waves, not just in terms of the time, but in terms of degrees. So that's going to be a specific phase angle, and we'll get to it, and I'll show this in another video, but the sine wave is going to be mapped out all the way from 0 to 360 degrees. Right in the middle, the sine wave is 180. Here's 270. Here's 90 degrees. And so we'll be able to talk in terms of where we are in a sine wave in terms of degrees. If I was right at this point, I'm at 90 degrees in that sine wave. I can calculate, though, any point in that sine wave. It's pretty easy. So, for example, this one that I circled here, if I want to know what phase angle, and that's that Greek symbol theta is what we use for phase angle. Where am I in that sine wave in terms of degrees? The answer to that is wherever you are in terms of time out of the period, the total time, is the same place that you are in terms of degrees out of 360. So that's a little formula that we'll use over and over again, because your scope can't measure degrees, but it can certainly measure time with vertical cursors. Do you see that? I can get my vertical cursors out here and measure this time t. I can measure that, and I already know this. So I've got this, and I know that the whole sine wave occurs over 360 degrees, and I'll help derive that for you at some point. Why is it 360 degrees? But if you can take it on faith for now. And then this is the only unknown left right here. So we can solve for it easily enough, right? And it's just ratios, isn't it? So now we know we can dissect the sine wave into instantaneous voltages. Any instantaneous voltage we want to know, we can find it in terms of degrees. And then there's some other things we can do with that too. We can then solve for the actual voltage there. That might be enough for this video, and then I'll kind of regroup and then we'll get into some more specifics. I think we'll wrap it there for now. Okay.